Okay, let me do 512 again, or at least let me cover the topics in 512 in a little more detail. The book doesn't do a great job of dealing with gears, and gears pop up a lot in torsional problems, so I figured I'd talk about it in a little more detail. So if you remember, the problem in 512 is that of a motor driving a shaft. That shaft has a small pinion that then mates with a larger gear that drives an output shaft. Okay? So let's talk a little bit about gears. So, by virtue of my children's Lego toys, I've kind of made a mock-up of this 512 problem. So here's the input shaft. My finger is the motor. Okay? And obviously, what they want to know is the torque needed to make this problem run in equilibrium. So if I apply, ignoring friction in the system, if I apply a torque on here and there's no load on this end, obviously this system will start to accelerate, right? So when they say equilibrium, they could mean, in fact, that there's an output torque I'm applying here with my left hand that stalls out the right torque. Or more commonly, what's probably thought of is that, here I put a wheel, like imagine it's driving a vehicle, and the motor actually drives the vehicle. So obviously, there's some drag force on the wheel. It could be the friction to the road, so my finger's trying to act like the road here. Or obviously, the vehicle has certain drag forces on it as well, and needs to overcome that. But there's some load on this output shaft that balances the input shaft, such that it spins with a constant angular speed. Okay? Now, if you look at the way the gear works, and I'll try to spin it slow so the video doesn't screw it up. The gear teeth, now I'm looking right at this point here, so this is the motor of my right hand, and I'm spinning the gear teeth. The gear teeth stay in contact, okay? So that means whatever distance, if I put a little, let me draw on the gears. Let's mark 2 points that are initially in contact. Can I do it with this thing? So there's two gear teeth that are in contact. Let's see if you can see it. I put a little black line on there. As it moves, those 2 points travel the same distance. Okay? Why? Because the velocity of a point on the small gear has to equal the linear velocity of a point on the bigger gear, because they're in contact. They can't slip, They can't slip. Whatever one moves, the other one moves. So that means the velocity point on one has to equal the velocity point on the other. So if I try to draw that, again, here is the two gears. Here's the smaller one that's the input, and then here's the larger one that's the output. So I'm looking at it down this way. What I'm saying is, I probably should draw a bigger picture. If I blow up this point, imagine I idealize the gear teeth acting like discs that are that are in contact with no slip. The amount a point here moves has to equal the same distance that a point here moves, okay? So these distances have to be the same.
These are the radiuses of the inner and the outer gears, respectively. I should probably make this one a little longer since it's a little bigger the way I drew it. Let's imagine I do it this way, right? And this goes to a center here. This is the radius of the outer disk, and this is the radius of the inner disk. Okay? This angle here is a very small amount that the input disk moves, and then here's a very small amount that the output disk moves. Those angles are not the same, but this distance is, right? So this distance here, call it S on the input side, equals S on the output side is equal to the radius on the output side times that little angle change. And likewise, this arc distance here, S on the input side, is the radius of the input times that angle change, right? These distances are the same. So they have to be equal. So setting these equal, this tells me that the angle change on the output is related to the angle change on the input through the radius. Okay, now if I divide by like a time increment, imagine these are angle changes. So let's put little deltas in here. So all right, so these little angle changes. Now if I divide both sides by time, I get an angle change per time. So these in the limit become the angular speeds in radians per second, right? So now I have the relationship between those speeds, okay? So this tells me this ratio of the outer radius over the inner radius scales. What am I doing? This is supposed to be inner. That's inner. That's outer. Okay? Solving for the outer angular speed from this equation, we get it's equal to the inner angular speed multiplied by the ratio of the inner gear radius to the output gear radius. Okay? So the way we drew this here, RO is bigger than RI, so this number is less than 1, so the output gear, the output shaft moves slower. And that's what you see here, right? So it's a little, I don't have such a great gear reduction on this one, but here you can see, let's look real closely at the two black points, and now they're lined up. Now I'm going to rotate it once so the inner gear moves around 360 degrees. Okay, so the point on the smaller gear is back to where it was, but you can see the point on the outer gear only moved here. Okay, so it moved around like 2/3 of the time, because I think this radius is sort of 1/3 of that one. Okay. Now, obviously, that translates also to the speed, okay? So this output wheel speed is slower than this input speed. Okay. As I did last time, obviously, since the power is conserved, when the speed goes up, the torque has to go down. So that means, or when the speed goes down, the torque goes up. So that means the speed and the torque have an inverse relationship. The speed goes up, the torque goes down. Speed goes down, torque goes up. So these guys are related as follows, okay? All right. Those are actually not bad relationships to remember. Let me show that, since sometimes the power argument isn't all the, it seems a little odd for people. It's, energy proofs are really very powerful, no pun intended, but sometimes they lack the believability sometimes because it seems a little magical. But
the other way to get the torque relationship is if I break up the gears separately. Let me get a piece of paper so I can use some space here. All right, so if I separate the gears and, separate it from a free body diagram, so if I apply an input torque that's counterclockwise, so here's the torque that's being applied here, okay? This gear is going to want to resist that torque, so it's going to apply a force, a contact force, onto this tooth such that it balances this out. And again, this has a radius of R inner. So doing sum of torques on this gear, the contact force times its moment arm has to equal the input torque. So that gives you the contact force. Now, you have an equal and opposite contact force on the output gear, okay? That's going to drive the gear around here, okay? And then what we're saying is, what is the output torque that resists that? Oops, I got it the wrong direction. Okay, and so this way, the output torque, well, let's draw it in the positive sense, okay? Let's draw it in the positive sense, and we'll see why. So I do this, then I get the output torque plus this torque, the torque from the contact force. So that's plus Fc times its moment arm, which is, that goes to 0. And in other words, the output torque is minus Fc times the outer radius, okay? Now we know Fc. From this one, I get that Fc is equal to input torque divided by the input radius. Taking this and putting it into here, we now get that the output torque is minus, oops, I'm sorry. Let me go up here. The output torque is minus the input torque times the outer radius over the inner radius. Okay? Which is what we had before. Now, why is there a minus sign? Well, the reason that there's a minus sign is to show you that it actually acts in the opposite direction. So actually what happens is you get a reversal of the torques from the way the gears work. So, I should have mentioned this earlier, but if you look, if I spin the input gear, the little one, counterclockwise, you can see obviously the output gear goes clockwise. So it means if I'm applying a counterclockwise or a positive torque on the input gear, okay, that means that the actual torque that the shaft outputs, that this wheel is going to drive, is actually going to be a clockwise or a negative torque, okay? Okay. Now you always got to be careful, if I am driving it this way, we stall it out, then, the shaft is still going to twist in this manner, right? It's still twisting in that sense, okay? But, technically, we should have a sign change on the torque, and technically, there should be a sign change on the speed, too, because it changes direction as well. So this falls into one of those situations where if you want to write the equations very precisely, you should put the minus sign in there. And then the sign should work out as long as you do it consistently. If you want to do it by feel and kind of drop the signs, that's fine as well, but sometimes don't forget the fact that they'll switch direction. When computing the stress again, though, it usually won't cause that much of a problem, okay?